Okay, in this video I'm going to talk about differentiation and integration of power series. So look at this, guys. This is the general form of a power series, right? This is a power series, and if you actually expanded, these are the terms of this power series. Notice that this is a function of x, right? So doesn't it make sense to find f prime of x, the derivative of that? So finding the derivative of a power series is same as differentiating each of these terms from left to right with respect to x, right? So we have a shortcut for that. So the derivative f prime is given as this. What do you do, guys? An here does not depend on x. So when you are differentiating with respect to x, keep an as a constant. X minus c to the n, you have to do the basic power rule, right? Bring the power down, subtract 1 from the power. And of course you would say, how about differentiating the inner part by chain rule, the derivative of x minus c, because c is a constant, the derivative of x minus c is 1. Multiplying by 1 doesn't change the result, and that's why we don't show that. So guys, here is the formula for the derivative of a power series. Keep the an does not depend on x, so treat that like a constant, and bring the n down, subtract 1 from the power. Done. I want you to notice one thing. The original power series starts at n equals 0, and here we had to increase the lower index by 1. Had we not increased the lower index and had we kept it as n equals 0, guys, 0 minus 1, that would give us a negative exponent. Okay, we want to make sure the exponent is always bigger than or equal to 0. So for that reason, this adjustment was necessary. Alright, now let's go back to the original power series. The original power series is here, and these are the first few terms of this original power series. Now, because this is a function of x, it makes sense to integrate that with respect to x. All you have to do is go ahead and integrate from left to right, term by term. And here's the shortcut, guys. Integral of f of x, of course, at the end of integration, you will get an arbitrary constant c. When you integrate that, okay, you're integrating with respect to x, right? An is a constant. Add 1 to the power, divide by the new power. Okay, when you integrate, add 1 to the power, divide by the new power. Basic power rule for integration. Now, we prefer to put the c in front of the summation rather than after the summation, because if you put a c here, guys, then you might mistake this for summing up infinite number of times, right? So to avoid that, we can put a c in front. Alright, so differentiating and integrating a power series is very easy. So we are integrating this as a function of x, guys, and differentiating this as a function of x, in other words, with respect to x. Okay, for differentiating, you bring the power down, subtract 1 from the power. For integrating, add 1 to the power, divide by the new power. Alright. The radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. Alright, guys. There's see, guys, the parentheses is not changing, right? So the center is going to be the same for the original as well as for the result obtained by differentiating, as well as the result obtained by integrating also. The radius of convergence of the series obtained by differentiating or integrating a power series also does not change, guys. It's the same as that of the original. The interval of convergence, however, may differ as a result of the behavior at the endpoints. Alright, guys. So I have a very simple power series here, f of x equals x to the power n over n factorial. I want you to find f prime of x. So guys, we have given this expansion, right? One way to find f prime of x is to go ahead and expand what you have here. Beg your pardon, go ahead and differentiate every single term you have here. Differentiate 1, you get 0. Differentiate x, you get 1. Now, this is 1/2 x squared, right? When you differentiate, it becomes 1/2 times 2x. This is 1 over 3 factorial x cubed. When you differentiate, that becomes 3x squared. 1 over 4 factorial, a constant. When you differentiate, that becomes 4x cubed. And you get that. Alright guys, so look. This is going to be 1 plus, that's going to be x plus, what's 3 over 3 factorial? Remember guys, 3 factorial is 1 times 2 times 3. The 3's cancel. You will have 1 times 2 left. 3's cancel, so you have x squared. 1 times 2 will contribute to 2 factorial. 4 and the 4 factorial cancel. You will have 1 over 3 factorial times x cubed. So we can put it as x cubed over 3 factorial. Notice something guys. You started off with f of x. You expanded and got a few terms. You found the derivative of each of these terms and you ended up with this. What are you noticing? Isn't f dashed of x exactly same as your f of x? Right? This is exactly same as your f of x. And we know when that happens, right? What function differentiated is equal to itself? Isn't that e to the power x? So our guess in this case is f of x equals e to the power x. Okay, you were not asked to find the function, but we were able to figure out what the function was using calculus 1, because we know the derivative of e to the power x is itself, isn't it? So we started off with f of x, we differentiated, we got f of x back, so that f of x must be e to the x. So guys, that's one way to come up with the derivative. Another alternative way is this. You have f of x given here, which is sigma n equals 0 to infinity x to the n over n factorial. Okay, now I want to find f dashed of x. Now how do you do f dashed of x, guys? 1 over n factorial is a constant. You are going to differentiate with respect to x. Bring the power down, and then you go ahead and subtract 1 from the power. That bring the power down, and the new power is x to the power n minus 1. Okay, and I told you when you rewrite the index, make sure the exponent starts with 0 or bigger. So for that reason, we have to increase the lower index by 1. So 1 minus 1 would be 0, right? So it won't be a negative exponent. If you didn't change that to 1, guys, if you kept it as 0, 0 minus 1 is negative. So we only define it for exponents bigger than or equal to 0. Alright, so guys, what is f dashed of x equal to here? Sigma n equals 1 to infinity n over n factorial. Guys, what is n over n factorial? N factorial is 1 times 2 times 3 times plus a bunch of numbers times n minus 1 times a bunch of numbers times n minus 1 times n, right? The n's cancel. So you will have n minus 1 factorial here. Okay, that's your f prime. Now we are probably starting to wonder, how is this f prime same as my original f in this question? Well, it's just a matter of rewriting, guys. Your original f is starting at n equals 0. If we want to start at n equals 0, that is fine. So what is happening, guys? You are you are decreasing the lower index by 1. So to balance that, go ahead and increase the n by 1 on the inside. If you increase it by 1, you get n. If you increase it by 1, you get n again. And of course, that's factorial. So these two are same, guys, except that we have rewritten with different lower index. I wanted to rewrite to show you f prime of x turns out to be exactly same as f of x. Okay, that happens when the f is e to the power x, right? Alright, I just wanted to show you, you get the same derivative either way, either by differentiating the terms of the expansion or by differentiating the series itself. Find the interval of convergence for each of the following. Okay, guys, you have f of x given. Here is the power series for the function f. Okay, now you have to find the interval of convergence for the integral of f of x, for the original f of x, for the derivative of f of x. Okay, So let's start with A. What is the integral of f of x? Okay, now we know that when we integrate, we get a constant c, right? Let's put the c in front. Go to f of x and integrate it. How do you integrate it? Okay, 1 over n here, guys, is a constant. That n doesn't change because you are integrating with respect to x. What are you going to do? You are going to add 1 to the power, divide by the new power. Okay, and this is infinity, and this is n equals 1. Okay, you don't have to increase that to 2 because when n is 1, the exponent is positive. Alright, now what we are going to do is, guys, test this for the interval of convergence. You don't have to worry about c. Why? C is some constant, right? So that is constant. So if this converges, then that's added to the constant, still converges, right? So all you have to do is take the series and test this for interval of convergence. Okay, test the series for interval of convergence. How do we start that? We are going to start by using the ratio test, right? So use the ratio test. Alright, so guys, what do we need? We need the limit. Have a look at this one, guys. What is the center? Center is still x equals 0, right? So for x not equal to 0, in other words, for values of x other than the center, for values of x other than the center, limit as n goes to infinity. What is a n plus 1? Increase n by 1. So it's going to be n plus 1 plus 1, n plus 2. This is n plus 1. This is n plus 1 plus 1, that is n plus 2. Okay? Flip it and multiply n times n plus 1 over x to the power n plus 1. Alright, guys, simplify this. What's getting cancelled out here? Notice that n plus 1 and n plus 1 are gone. And also notice that we have an extra x in the numerator because the power on x in the numerator is 1 higher than the power on x in the denominator. Besides that, we have n over n plus 2 as well. Alright, so let's try to find the limit, shall we? So the limit of that, when you take the limit of x inside the absolute values, it is absolute value of x. Limit of that is 1. So guys, by ratio test, the limit of the series, by ratio test, the limit of the ratio, okay, for the series resulting from integrating the original is absolute value of x. We know that the series converges when the limit of the ratio is less than 1. That means when x is between negative 1 and 1. And we also know from our second video that we must check the endpoints. Okay, check endpoints one by one. Okay, guys, so I'm going to say when x is negative 1, when x is negative 1, okay, remember guys, we are checking integral of f of x, right, for the interval of convergence. So go to the series resulting from integrating f of x. That's this series. Okay, in that series, we are now checking the two endpoints. The first endpoint is negative 1. Replace x by negative 1 here. Okay, when x is negative 1, you get sigma n equals 1 to infinity, negative 1 to the power n plus 1 over n plus 1 times n. Okay, guys, what can you say about this series? When x is negative 1, the series turns into an alternating series whose nth term is 1 over n plus 1 times n. Alright, so we are going to say do alternating series test on this. Remember, for the alternating series test, you must check two conditions. Number one, limit as n goes to infinity of an, that is, limit as n goes to infinity of 1 over n times n plus 1, and that limit is 0. Okay, this is your an, right? So that limit is 0, so the first condition is met. Second condition, is an plus 1 less than or equal to an for all n, right? So have a look. This is your an, replace it by n plus 1. So 1 over, this becomes n plus 2, and the other becomes n plus 1. That clearly is less than or equal to the an we have here. Alright, so we will say converges when x is negative 1. That is the left-hand endpoint. Now check the right-hand endpoint. What's the right-hand endpoint? Scroll back up. Okay, right-hand endpoint is x equals 1. So when x equals 1, what do you have to do? Go ahead and replace x by 1 in the series obtained by integrating f of x. N equals 1 to infinity. I'll show you where to plug in, guys. Now, look here. This is where you have to plug in 1. That's the series obtained by integrating f of x. Come down, replace x by 1. 1 to the power n plus 1 over n plus 1 times n. If you simplify this, guys, 1 to the power n plus 1 is simply 1, and this is n squared plus n. So that is the series you end up getting at the right-hand endpoint x equals 1. What is a good test on this? Can we do a direct comparison test? Compare with, I will say 1 over n squared. First of all, guys, for the direct comparison test, let's compare the nth terms of the two series. Which one is smaller? This one is smaller, right? Because the denominator here is larger. So if you could show that this one converges, in other words, if the larger series converges, then the smaller series must converge by the direct comparison test, right? So what do we know? This is a p-series with p equal to 2. So this one converges by the p-series test. Okay, the larger series converges by the p-series test. Now, what can we say about sigma 1 over n squared plus n from n equals 1 to infinity? This one converges by direct comparison test. Alright, guys, so let's go ahead and conclude. The series obtained by integrating f of x, mind you guys, f of x in this question is a power series. Okay, f of x in this question is a power series. So we are asked to find the interval of convergence, first of all, for the integral of f of x. We did the ratio test. We got x between negative 1 and 1. Then we checked the endpoints. We confirmed that it converged at the left-hand endpoint and also at the right-hand endpoint. So the integral of f of x converges on negative 1, 1 at both endpoints, guys. Please be sure to put brackets. Okay, that completes part A. Part B. What do we have to check? Find the interval of convergence for the function f of x. This is the function f of x. So you don't have to integrate, you don't have to differentiate. Go ahead and find the interval of convergence for the original f of x. Part B. Okay, f of x equals sigma n equals 1 to infinity x to the n over n. Okay, what's the center for that, guys? Center is 0. Okay, we know that every single power series converges at its center. So let's try and figure out for what other values of x the series converges, right? So for x not equal to center, for all other values of x, I mean, find the limit as n goes to infinity of the ratio x to the power n plus 1 over n plus 1. Remember, we are doing the ratio test on the series, divided by an, flip and multiply. And notice that when you simplify that, you have an extra x in the numerator, and then we have n over n plus 1, right? Now, when you take the limit of x inside the absolute value signs, it comes out as absolute value of x. When you take the limit of the fraction, it is 1. So guys, the limit of the ratio for the power series denoted by f of x is absolute value of x. But what does the ratio test tell you guys? The series converges when the limit of the ratio, in this case when absolute value of x is less than 1, that means x must be between -1 and 1. Alright? So we know the series definitely converges for x between -1 and 1. What we are not sure about is the endpoints. You must check the endpoints. Okay? When x is -1, guys, your original f of x becomes -1 to the n over n. Okay? This is an alternating series with an equal to 1 over n. So let's do the alternating series test on this. By now you should know what the result is going to be. Two conditions need to be checked. Limit as n goes to infinity of an, that is limit as n goes to infinity of 1 over n, that is 0. Okay. Number 2 is an plus 1 less than or equal to an. 1 over n plus 1 is clearly less than or equal to 1 over n. That is done. So because both conditions are met for the alternating series, so we would say series in part B. In other words, the series for the function f converges when x is -1. Now check the other endpoint. When x is 1, the series in question goes to 1 to the power n over n, that is sigma n equals 1 to infinity 1 over n. Okay, and what is that? This is a divergent p-series because the p-value here is 1. We know that when the p-value is 1, the series diverges by the p-series test. So the series in part B, in other words the original series, diverges when x is 1. So guys, what can we say about the interval of convergence of f of x? Okay, the interval of convergence of f of x is, what is it guys? It converged at -1, it diverged at 1. So half closed, half open, and the ratio test told us that it was convergent for all values of x between -1 and 1. Now, before we wrap up the problem, it has part C. Okay, realize it has part C. For part C, guys, you are asked to find f dashed of x. Okay, let me write f of x first for you. For part C, okay, f of x in question is the summation of x to the n over n. Okay, in part C, you are asked to find the interval of convergence for the derivative, guys. Okay, what is the derivative? Okay, 1 over n is a constant. You bring n down, n as in the exponent on x. You bring the exponent down, subtract 1 from the power. Okay, and then n equals 1 is fine, guys, because when n is 1, then exponent is not negative, so you don't have to increase the lower index by 1. But when you simplify, it is n equals 1 to infinity x to the n minus 1. And of course the center here is still 0. We know that this series is convergent at its center. The question is, where else is it convergent, right? So do the ratio test. Okay, do the ratio test. Alright guys, what are you going to get? Okay, we are going to do the ratio test for x values other than 0, right? Okay, so limit as n goes to infinity of an plus 1 over an, which is limit as n goes to infinity of add 1 to the power. Okay, divide by an, and notice that we have an extra x in the numerator. Numerator power is 1 more than that of the denominator. Okay, so this is the limit of the ratio, and that's going to be absolute value of x. It does not depend on n. Converges when absolute value of x is less than 1, meaning x must be between negative 1 and 1. Now you must do the endpoint check to determine whether the series resulting from differentiating f of x is convergent at the endpoints. Alright, let's go ahead and check the endpoints. When x is negative 1, alright, this is the series resulting from differentiating your original f of x. And we are trying to check the interval of convergence for this series. Replace x by negative 1, raise it to the power n minus 1. So when x is negative 1, we are going to have negative 1 to the power n minus 1. Alright guys, negative 1 to the power n minus 1. When n is 1, 1 minus 1 is 0. Negative 1 to the 0 is 1. And then it's negative 1, and then it's positive 1. This is a geometric series with r equals 1, with r equals negative 1, absolute value of r is 1. That means it diverges. But when x is 1, the series resulting from differentiating f of x turns to 1 to the power n minus 1. That also is a geometric series whose r is 1, absolute value of r is 1, so diverges. So guys, at both endpoints, f of x diverges. So guys, I'll say, at both endpoints, f dashed of x diverges. So I'll say interval of convergence for f dashed of x is negative 1, 1. Okay, the ratio test gave us negative 1, 1. We checked the endpoints failed. So the interval of convergence for f dashed of x is strictly between negative 1 and 1. So guys, this is the interval of convergence for f dashed, negative 1 and 1, open interval. Interval of convergence for the original is half closed, half open. Interval of convergence for the integrated series is closed. Okay, so I just want to make a note here, guys. Of the three series, the series for the integral, the series for the original function f, and the series for the derivative, of the three series, the one for the derivative is the least likely to converge at the endpoints. Okay, as you can see, at the endpoints the derivative failed, right? Of the three series, the one for the derivative is the least likely to converge at the endpoints. In fact, it can be shown that if the series for the derivative converges at the endpoints, then the series for the original will also converge there. Okay, in fact, it can be shown that if the series for the derivative converges at the endpoints, then the series for the original will also converge there. Alright guys, it's time for us to practice some problems in the next video.